Hey everyone, try something with me for a second. Imagine you wake up tomorrow and the zero on your keyboard is gone. Not broken, just gone, like it was never invented. Your bank app cannot show you an empty balance. A price tag that used to say 100 has no way to say it anymore. And the whole idea of a ones place, a tens place, a hundreds place quietly falls apart, because the thing that holds an empty slot open is missing. Back in school, most of us met zero on day one, and nobody made a fuss about it. It sits at the front of the number line. It is where every ruler starts. It looks like the most obvious idea in mathematics. It took humans thousands of years to agree that nothing is a number. The Egyptians built pyramids without it. The Romans ran an empire without it. Greek mathematicians proved theorems we still teach today, and none of their number systems had a digit for nothing. Look at how a Roman writes the year 1888. M, D, C, C, CLXXXVII. 13 symbols to say one number, and not one of them is a placeholder, because in that system there is nothing to hold a place for. Here is the part that took so long. Everybody could see emptiness. An empty bowl is not a hard idea. A shepherd with no sheep knows he has no sheep. The hard part was something else. The hard part was treating that emptiness as an object. Something you could write down, put in a column, add, multiply, and hand to somebody else as an answer. For Greek mathematics, that was close to a contradiction. Their math grew out of geometry. Lengths you could draw, areas you could shade in, shapes you could hold in your hand. So what length is nothing? What do you do with a quantity that has no size? That leaves us two questions, and they turn out to be the same question wearing different clothes. Why was zero so hard to accept? And once we finally let it in, why did it immediately start breaking the most ordinary rule in arithmetic, the rule for dividing one number by another? To find out, we have to go back to a piece of wet clay in ancient Mesopotamia, where zero first tried to show its face. Start with something small. Write 35. Now write 305. Same digits at the ends, completely different numbers, and the only thing doing that work is the zero sitting in the middle. Take it out, and 305 collapses into 35. The zero is not saying nothing. It is saying there is nothing in this column, and that is information. The Babylonians got there first. By around 300 BC, their scribes were writing two small slanted wedges into the middle of a number to mark an empty slot. Their system counted in 60s rather than 10s, but the idea is the one you just used with 305. They stopped halfway, though. They never wrote that mark at the end of a number, so a 2 and a 2 that really meant 2 times 60 came out looking exactly the same on the tablet. If you were a merchant reading a receipt, you had to guess from context whether you were owed 2 sheep or 120. The mark was a repair for the middle of a number. It was not yet a number of its own. The jump happened in India. In the year 628, an astronomer named Brahmagupta wrote a book called the Brahmasphutta Siddhanta. The whole thing is in verse, written to be recited out loud, and inside it he does something nobody had done before. He gives zero a name, shunya, meaning empty, and then he writes down rules for it, the way you would for any other number. Add zero to a number, and the number does not change. Multiply anything by zero, and you get zero. That is the moment the empty column becomes a thing you can compute with. Then he reaches division, and he slips. He writes that 0 divided by 0 is 0. It sounds reasonable. Nothing shared among nobody should be nothing. Hold on to that sentence, because in a few minutes you will see exactly why it fails, and the failure is more interesting than the rule. Historians still argue about what Brahmagupta actually meant there, and whether he was claiming what a modern reader hears. What nobody doubts is that the sharpest mind of his century walked straight into division by 0, and came out with the wrong answer. About 500 years later, another Indian mathematician, Bhaskara II, tried to patch the hole. In his algebra book, the Bija-ganita, written around 1150, he takes a number divided by 0 and calls the result kahara. He says 3 divided by 0 is an infinite quantity, and he describes it with an image from his own world. Kahara is like Vishnu. Creatures pour into the god and pour back out of him without end, and the god is not changed by any of it. Add something to infinity, takes something away, and infinity does not move. That idea traveled. In 1202, a mathematician from Pisa named Leonardo Fibonacci published the Liber Abaci and carried the Indian and Arabic numerals, 0 included, into Europe. So why did we not simply keep Bhaskara's answer? Why does modern mathematics refuse to say that 1 divided by 0 is infinity? Because dividing by 0 does not fail in one way. It fails in 2 completely different ways, and telling them apart is where this gets good. If you ever asked a teacher why you cannot divide by 0, and the answer you got was that it is just the rule, you had every right to walk away annoyed. That is not an explanation. That is a door being closed. And the real reason is far better than the rule. Start with what division actually means. When you say 12 divided by 3 is 4, you are not doing a brand new operation. You are asking a multiplication question backwards. You are asking which number times 3 gives you 12. The answer is 4, so that is the answer to the division too. Every division you have ever done is that question in disguise. Now put it on a table. You have 12 chocolate bars, and you want to share them out evenly among the friends in the room. 3 friends walk in. Everyone gets 4 bars. 12 divided by 3 is 4. Now the first strange case. Nobody walks in. The room is empty. You still have your 12 bars, and you ask the question anyway. How many bars does each person get? Sit with how odd that question is. There is no person. There is no each. And the arithmetic says exactly the same thing. You are looking for a number that multiplied by 0 gives you 12. Try 5. 5 times 0 is 0. Try 1,000,000. Still 0. Try any number you can name, and you get 0, because that is what multiplying by 0 does. Nothing you could ever write down will give you 12. There is no answer. Not a hard answer, not a hidden answer. The set of correct answers is empty. That is what mathematicians mean when they call 12 divided by 0 undefined. Now the second case, and this is the one that catches people. You have 0 chocolate bars and 0 friends. Same question. How many bars does each person get? Backwards again. You want a number that, multiplied by 0, gives you 0. Try 1. 1 times 0 is 0. That works. Try 5. 5 times 0 is 0. That works too. Try 999. Works. Try any number in the universe and it works every single time. Look at what just happened. The first case had no answers at all. This one has all of them. Every number is equally correct, so no number can be singled out as the answer. Mathematicians call 0 divided by 0 indeterminate, and that word is doing real work. It does not mean unanswerable, it means undetermined. What you were given is not enough to pin the answer down. 2 failures, opposite in shape. One is an empty room. One is a room so crowded that nobody can tell you who is in charge. And Brahmagupta's slip was reaching into that crowd, pulling out one answer and calling it the winner. But people are stubborn, and mathematicians are worse. Somebody was always going to ask the obvious next question. What if we force it anyway? What if we do what Bhaskara did? Plant a flag, declare that 1 divided by 0 is infinity, and see what breaks. Let us take that deal seriously. Suppose we allow it. 1 divided by 0 is infinity, and 2 divided by 0 is infinity as well, since dividing by nothing ought to blow up either way. Now run both of those backwards, with the same rule we have been using all along. 1 divided by 0 being infinity means that 0 times infinity gives you 1, and 2 divided by 0 being infinity means that 0 times infinity gives you 2. Same thing on the left. Two different things on the right. So 1 equals 2. That is not a curiosity. If 1 equals 2, then every price is every other price. Every measurement is every other measurement. And arithmetic loses the ability to tell any two quantities apart. One convenient definition, and the whole building comes down. There is a second way to see it, and it is gentler. Instead of jumping straight to 0, walk toward it. Take 1 and divide it by numbers that keep shrinking. 1 divided by 0.1 is 10. 1 divided by 0.001 is 1,000. 1 divided by 0.000001 is 10000. The smaller the divisor gets, the bigger the answer gets, with no ceiling anywhere. It really does look like it is heading for infinity. Now come in from the other side, through the negatives. 1 divided by negative 0.1 is negative 10. 1 divided by negative 0. 001 is negative 1,000. 1 divided by negative 0.000001 is negative 1000000. The same shrinking distance to 0. But now the answers are falling, not climbing. Picture the graph of y equals 1 over x. To the right of the 0 line, the curve rises, steeper and steeper, shooting off the top of the screen. To the left it plunges, straight off the bottom. And at 0 itself, the curve simply is not there. There is a clean vertical tear through the middle of the picture, one branch racing up toward positive infinity, the other racing down toward negative infinity, and the two of them never meeting. That is the real trouble. It is not that the answer is too big. It is that the approach from the right and the approach from the left disagree about which direction the answer even lies in. Any single value you wrote down would have to be both at once, and nothing is both. So notice what the rule really is. Nobody sat in a committee and banned division by 0 to make school harder. The ban follows from two things we quietly decided we wanted. We want each division to have exactly one answer, and we want the ordinary rules of arithmetic to keep holding, so that 1 stays different from 2. Hold those two wishes at the same time, and the ban is not a choice at all. It is forced, which leaves one door open, and it is a strange one. If the ban comes out of what we decided we wanted, then a different set of wants would give a different rule. Everything we have done so far lives on a flat playing field, the ordinary number line running away forever in two directions. What happens if we bend that field in? I want to be honest about how this is going to sound. We hit a wall, and now we are going to change the shape of mathematics itself so the wall is not there anymore. That should feel like cheating. It is not, and the reason it is not is the real lesson of this video. The rules of arithmetic are not handed down by the universe. They are tools built by people for particular jobs. Change the job, and you are allowed to rebuild the tool. You just have to pay for it, and we will get to the bill. Here is the construction, from a mathematician named Bernhard Riemann in the 19th century. Take the flat plane of numbers and lay it out like a tabletop. Now rest a clear glass ball on it, so that the very bottom of the ball, the south pole, touches the point 0. Now shine a light from the top of the ball, the north pole. Every ray leaving that north pole passes through the surface of the ball and lands somewhere on the tabletop. That gives you a pairing. Every point on the plane gets 1 point on the ball, and every point on the ball gets 1 point on the plane. Watch what that pairing does. Numbers close to 0 end up near the bottom of the ball. Numbers further out sit higher up. And as you travel further and further from 0 along the tabletop, your point on the ball creeps closer and closer to the North Pole, without ever quite arriving. So the North Pole is the one place with nothing on the plane to pair with. It is where you would land if you could go infinitely far out, and it does not matter which way you set off. Go right along the positive numbers, and you climb toward the North Pole. Go left along the negatives, and you climb toward that same North Pole. Remember the tear in the graph. Positive infinity leaving the top, negative infinity leaving the bottom, no way to join them. On this ball, they are not two places. They are one point. The two ends of the number line have been curled around and sewn together at the top. And with that stitch, the thing we could not do becomes ordinary. On this sphere, 1 divided by 0 has an answer, and the answer is that single point at the North Pole, the one we call infinity. It is not a fudge. It is consistent. It behaves properly. And complex analysis has been working with it for well over a century. Now the bill. The moment you let infinity be a genuine point, it stops being a number in the way you are used to. Ask what infinity minus infinity is on this sphere, and there is no answer. Ask what 0 times infinity is, and there is no answer there either. You rescued division, and the cost came out of subtraction and multiplication. That is the shape of the whole deal. Mathematics does not hand out new freedoms for free. Every time you stretch a system to make one forbidden thing work, something that used to work quietly stops working. I should say that to keep this picture clean, I have smoothed over some technical detail about the plane Riemann was actually standing on, which is the complex plane rather than the ordinary number line. The projection and the trade are exactly as described. And that trade is not just something sitting on Riemann's page. Your phone is making a version of the same decision billions of times a second. A computer does not get to shrug. Somewhere in a spreadsheet, a game engine, or the flight software of an aircraft, some number is going to end up divided by 0. If the machine froze every time that happened, nothing would ever finish running. So engineers had to make a call. In 1985, they wrote it down in a standard called IEEE 754, which is the agreement almost every processor on Earth still follows for handling decimal numbers. And look at what they chose. They did not pick one answer for division by 0. They picked two, and they split them along exactly the line we drew earlier. Divide a normal number by 0, something like 1.0 divided by 0.0. And the machine hands back infinity. That is the undefined case, the empty room, and the standard takes the same road Bhaskara took. It reports the blow-up and keeps going. Divide 0.0 by 0.0, and you get something else entirely. You get NaN, which stands for not a number. That is the indeterminate case, the room where every answer is correct. The machine is telling you that the question never narrowed anything down. Then comes the part that looks like a bug and is not. Ask the computer whether NaN equals NaN, and it says false. That value is not equal to itself. There are two reasons, and both of them are good. The practical one is a piece of history. In the early days, there was no built-in function for asking whether something is a NaN. So the standard made NaN the one value in the entire system that fails a comparison with itself. That handed programmers a test that works anywhere. Compare a variable to itself. If it comes back false, you have caught a NaN. The deeper reason is about what NaN actually means. It is not a number that went missing. It is a record that a computation failed. 0.0 divided by 0.0 produces 1. Trying to take the square root of a negative number produces 1, 2. Those are two completely different failures. Saying they are equal would be claiming that one broken calculation is the same as another broken calculation, and there is no sense in which that is true. So the standard refuses to say it. That is a design decision with a philosophy inside it. When a machine cannot determine an answer, the honest move is not to invent one. It is to hand back a value that keeps announcing, everywhere it travels, that something here was never determined. From wedges pressed into wet clay to the silicon in your pocket, the argument about zero turns out to be the same argument, asked again with better equipment. Look back at the road. We started with civilizations that built empires without a symbol for nothing. We watched Babylonian scribes prop open an empty column with two small wedges. We watched Brahmagupta turn that gap into a number and then stumble at the very first division. We took apart what division really asks and found two different ways for it to fail. We watched a graph tear itself in half at zero. Then we curled the number line into a sphere, sewed the tear shut, and paid for it out of subtraction. And we found the same bargain living inside a standard written for computers in 1985. So here is where that leaves the rule you were handed in school. You cannot divide by zero is not a wall the universe built to keep you out. It is a choice, and the choice is ours. We make it because we want something else more. We want a system where every question has one answer and where one never turns into two. Zero is not being punished. It is being asked to sit outside one particular operation so that everything else stays trustworthy. And when we are willing to pay, the door opens. Step onto Riemann's sphere, give up a few of the old comforts, and dividing by zero becomes an ordinary Tuesday. That is what mathematics actually is. Not a book of absolute laws, but a long series of trades, each one made on purpose, each one with a price written next to it. The interesting question was never whether you are allowed to divide by zero. It is what you are willing to give up in exchange. If the question you asked as a kid finally got answered properly today, consider subscribing to Axiom Code and leave a comment with the next piece of mathematics you want us to take apart. See you in the next one.